Okay, so welcome back to this next video in which we are discussing voltage-gated ion channels. Okay, right, so we've now discussed the action potential, which we did in order to motivate our now more in-depth discussion of the different classes of voltage-gated ion channel. Okay, right, so the first type of voltage-gated ion channel that we're going to study in detail then is going to be the voltage-gated potassium channels, okay, which for short we can abbreviate down to the VGKCs for voltage-gated and then potassium channels. Okay, right. So what we're going to do then is we're firstly going to discuss the structure of a voltage-gated potassium channel, okay? Then what we will talk about is the diversity of voltage-gated potassium channels, because what we'll see is that voltage-gated potassium channels is a whole family, basically. There's not just one voltage-gated potassium channel. It would be beautifully simple if there was just one voltage-gated potassium channel, but there is an absolutely huge number of voltage-gated potassium channels, okay, and we'll see the massive great diversity. Now they all have the same basic core structure, okay, but they will all differ slightly from each other, okay, so the proteins out of which they are built will fundamentally have different primary amino acid sequences, even though the grander structure, the bigger scale structure of the proteins actually resembles one another. Okay, right, so we'll have a look at the diversity of voltage-gated potassium channels then, okay, and then what we'll also look at is the gating mechanism. So we'll look at how depolarization of the electrical potential difference across the cell membrane from negative 65 millivolts to something around negative 40 millivolts will actually lead to the voltage-gated potassium channels opening, and we'll therefore discuss how prior to the electrical potential difference across the cell membrane being depolarized, the voltage-gated potassium channel is closed. Okay, right, so let's start off then with a discussion of the structure of voltage-gated potassium channels. Okay, now the way I'm going to do this is I'm going to gradually draw you more and more complicated pictures which get closer and closer to actually looking how these things actually look, basically. They get closer and closer to the truth. Okay, and remember we do actually have X-ray crystal structures that are absolutely beautiful of these things, and therefore we do know what these things look like. Okay, so I'm going to start off with very basic pictures, which are so basic that they're almost untrue. Okay, but they will serve to highlight key concepts, and then we'll develop towards the more complicated picture. I think that if I just threw the more complicated picture at you initially, it would be quite difficult to take in all at once, so we'll build up towards it. Okay. Right, so the first picture then that I'm going to draw you of a voltage-gated potassium channel is going to be so basic that it's almost untrue, but it will highlight a key concept that I want to get across. Okay, so let's let these two parallel lines then that I'm drawing here represent the cell membrane of our neuron, maybe. Okay, so let's let this be the extracellular fluid side, and this be the cytoplasmic side. So this is the outer leaflet of the phospholipid bilayer, and this is the inner leaflet of the phospholipid bilayer. Okay, now let me draw a voltage-gated potassium channel sitting in the membrane here. Okay, so I'll just draw it as a great big cylinder sitting in the cell membrane like so. Okay, now because it's an ion channel, I'll put a little pore down the middle, okay, and then I'll continue the cell membrane on the other side. Okay, right, so what's the key concept then that I want to get across in this picture? Okay, well the key concept that I want to get across is that these voltage-gated potassium channels are not just a single protein. Okay, they are not just constructed out of one massive great polypeptide. Okay, instead they are multiple proteins that have all been stuck together, basically. Okay, specifically you have 4 separate proteins that have been stuck together to build the full voltage-gated potassium channel. So let me now divide up this cylinder into 4 separate portions, which will represent the 4 separate proteins that have all been joined together to make our voltage-gated potassium channel. Okay, right. So it is basically a tetramer, a four-membered structure, okay, rather than an individual protein. Okay, so here is 1/4 of the voltage-gated potassium channel, here is another quarter, and the final quarter. Okay, and each one of those is a separate protein, basically. So you bring together these four proteins, and then you've got your voltage-gated potassium channel. Okay, you can't just bring together 3 of them and make a voltage-gated potassium channel. It has to be 4. So that's the first key concept, that it's not just a single protein. It is instead a tetramer of 4 proteins that have all been joined together. Okay, now, these individual proteins then that make the voltage-gated potassium channel tetramer, okay, one of which I am now highlighting up in red here, these are called the alpha subunits of the voltage-gated potassium channel. Okay, and we'll see later there are also beta subunits of voltage-gated potassium channels. They are not shown on this picture yet, okay, because they are not actually essential. You do not need beta subunits to make a voltage-gated potassium channel. They are what are called accessory or auxiliary subunits. You can add them on, they change the properties of the voltage-gated potassium channel, but they don't need to be there in order for it to actually function as a potassium channel and as a voltage-gated potassium channel specifically. Okay, so in order to make a voltage-gated potassium channel, all you need to do is put together 4 alpha subunits. You don't need any beta subunits at all. Okay, so we will actually discuss the beta subunits much later on. Okay, when we've actually got enough understanding to understand what their function actually is. Okay, right. So voltage-gated potassium channels then, they are these tetramers of 4 alpha subunits of voltage-gated potassium channels put together to make this structure which has a pore for potassium moving down the middle. Okay, right. So now what I want to do is I want to pull out an alpha subunit of a voltage-gated potassium channel. So let's say we're going to pull this alpha subunit out. Okay, and I want to now show you the actual membrane spanning topology of an alpha subunit of a voltage-gated potassium channel. Okay, so what do I mean by membrane spanning topology? Okay, well, these alpha subunits are going to be integral membrane proteins. They're going to have membrane spanning alpha helices. Okay, and I want to show you how many membrane spanning alpha helices it has, on which sides of the membrane are the N and C termini. All of that sort of information is what is meant by the membrane spanning topology. So I want to give you the core structure then of an alpha subunit of a voltage-gated potassium channel, and then what I'll do is I'll redraw what voltage-gated potassium channels actually look like. Okay, so how the 4 alpha subunits are actually arranged, because it isn't as simple as this, I'm afraid. Okay, part of it is this simple, but another part isn't. Okay, and we'll see how it's not that simple later on. Okay, right, so let me start then by drawing out the alpha subunit of a voltage-gated potassium channel. So once again, I'll draw the cell membrane as 2 parallel lines here. Okay, once again, this side will be the extracellular fluid side, and below will be the cytoplasmic side. Okay, and now what I'm going to do is I'm going to draw an individual alpha subunit of a voltage-gated potassium channel, and I'm going to highlight the key structural features. Okay, so basically the amino terminus of the alpha subunit of a voltage-gated potassium channel is inside the cell. It's on the cytoplasmic side of the membrane. Okay, then I'll represent the polypeptide just as a line. So this line is representing the polymer of amino acids. Okay, then there is a very important domain that is present in all the different types of alpha subunits of voltage-gated potassium channels. And we haven't actually discussed this yet, but we will later on discuss that there are loads of different types of alpha subunits of voltage-gated potassium channels. But the structural features that I'm showing you here apply for all of them, basically. Okay, so this first key box here, which I'll colour in red here, this is what's known as the T1 domain. Okay, and its full name is the T1 tetramerization domain. Okay, and that tells you what this domain is important for. It's important for holding the 4 alpha subunits of the voltage-gated potassium channel together. Okay, so what actually holds these 4 alpha subunits together when they form this tetramer? Well, part of that is this T1 tetramerization domain. Okay, and we will see that these domains do indeed tetramerize. So you've got 4 alpha subunits, each of them will have a tetramerization domain, and the alpha subunit tetramerization domains all do tetramerize together below the transmembrane portion of the voltage-gated potassium channel, and we'll see a picture showing that later on. Okay, right. Then we begin the membrane-spanning alpha helices. Okay, so here we go. There is the first membrane-spanning alpha helix, and I acknowledge that I have not drawn it actually as an alpha helix. If I was drawing it as an alpha helix, I would draw it in a spring sort of shape. Okay, however, if you do that, it makes the picture look horrendously more complicated. Okay, so I have drawn it as a straight line simply because that looks simpler. Okay, but where you cross the membrane, whenever a protein crosses the membrane, it usually adopts an alpha helical structure. Okay, and indeed, in all of the transmembrane portions that we're going to see, they are alpha helices, even though I will not be drawing them as alpha helices. Okay, right. So I will draw out all the other alpha helices before I actually label up the different alpha helices. Okay, right. So that's the first membrane-spanning alpha helix. There's the second. Here's the third. Here's the fourth. Here's the fifth. Then you have a weird structure now, a new structure. Okay, what's going to happen is the polypeptide is going to plunge into the membrane, okay, and the first descending portion in which it plunges into the membrane is going to be alpha helical in nature. So this portion, this descending portion going into the membrane, is going to be alpha helical, and then it's going to plunge back out, okay, so it's not going to make it all the way through the membrane, it's going to now plunge back out, okay, and this portion where it's actually going up, this ascending portion, this actually isn't going to be alpha helical, this is going to be straight. Okay, and this is going to be important later on when we come on to the actual permeation and selectivity mechanism, because this ascending portion, this little ascending portion here, is actually the portion that is going to line the pore. So every single one of these 4 subunits is going to contribute this ascending portion of this little re-entrant loop here, okay, to line the pore, at least on the extracellular side. Okay, of course it can't line the pore all the way through because it doesn't actually go all the way through the membrane. Okay, then after that structure, you've then got the 6th membrane-spanning alpha helix here, which is the portion that then lines the pore further below, the internal aspect of the pore. But don't worry, we will discuss all of this in much more detail later on. Okay, right, and then there's no more important domains after that, so we'll just finish up with the C-terminus here. Okay, right, so let me firstly now tell you the names of all of these membrane-spanning alpha helices, and I'm also going to colour code them because I now want to draw you a more accurate picture of a voltage-gated potassium channel, and I want to show you where all of the membrane-spanning alpha helices actually are positioned in this voltage-gated potassium channel structure. Okay, right, so I'm going to colour code the first membrane-spanning alpha helix up in green there, okay, and that's called the S1 membrane-spanning alpha helix, and in fact all of these alpha helices are labelled with the same nomenclature, S and then the number, okay, so S1 is there in green, okay, then the second membrane-spanning alpha helix, that will be called S2, okay, so this is S2, and once again I'll colour code it, so it's there in blue. Okay, then we'll have S3 here in red. Okay, so that's S3. Then the 4th membrane-spanning alpha helix, sticking to the nomenclature, that will be called S4. We'll have that colour coded in an orange here. Okay, and we're running out of space for the annotations, but we'll just sort of loop round. Okay, now I'm going to break with tradition and actually colour in a portion that isn't the next membrane-spanning alpha helix. I'm going to colour in this little linker here between the 4th membrane-spanning alpha helix and the 5th membrane-spanning alpha helix. Now, although I haven't shown it on this picture, that linker between the 4th and the 5th membrane-spanning alpha helix is actually much bigger than these other linkers that we've got here. Okay, it's much, much bigger, and it actually contains an alpha helix itself. Okay, so some people will draw this picture where they separate these two helices much more, S4 and S5, much more, and they show this linker much longer, basically. Okay, so if you imagine extending this out like so, and then having the rest of this, that's what they draw this picture as. Okay, and indeed this portion is much longer, and it's actually going to play an incredibly important role in the gating mechanism, which is why we are highlighting it in. Okay, so what is this called? Well, this is called the S4, S5 linker, quite simply because it is the linker between the fourth membrane spanning alpha helix, S4, and the fifth membrane spanning alpha helix, S5. Okay, so watch this space. We will come back to that linker in just a moment. Okay, right, now let's continue on with the membrane spanning alpha helices. So we'll have S5 there, coloured in turquoise. Okay, so this is S5. Okay, and now I'm going to label up this structure here. So we don't call this an S. Okay, this is what's called the P loop. Okay, so the entire loop here, from here to here, all of this is called the P loop. Okay, and the reason it's called that is that the P stands for pore, basically. Okay, and this loop is going to be the portion that actually lines the pore, basically, hence why it's called the P loop. However, I want to divide it up into two separate portions. Okay, the descending portion, which I'll have in vivid purple there, which actually forms an alpha helix called the P helix. Okay, so that descending portion that's plunging into the membrane, that's an alpha helix in nature, okay, called the P helix. Okay, and then the other portion I want to separate it into is the ascending portion, which I'll colour in yellow there, okay, which doesn't have a name, but which we will call the ascending P loop, basically. Okay, so we will probably refer to the P helix as the descending P loop, and I might just colour it in a bit more so that it shows up better, even though really it should just be the portion that's actually in the membrane. Okay, we will call this purple portion the descending P loop, and we'll call the yellow portion the ascending P loop. Okay, and the ascending P loop is the portion that's actually going to be lining the pore. Okay, and we will be dwelling on this a lot later on when we come to discuss permeation and selectivity. Okay, it's got a remarkable structure. Okay, right. Then I've run out of colours, so we're going to have to use colours that we've already used. We will colour now the final and sixth membrane spanning alpha helix in blue, and that's called S6. Okay, so there are all the different portions then of a alpha subunit of a voltage-gated potassium channel coloured in different colours. Okay, what I now want to show you then is how these alpha subunits are actually going to be arranged in the voltage-gated potassium channel tetramer. But before we just do that, let me just give you two other helpful things, okay, which is going to help us in our understanding of how these alpha subunits of voltage-gated potassium channels are going to actually assemble into the tetramer. Okay, so basically, people often divide these alpha subunits of voltage-gated potassium channels into two very distinct domains. Okay, so the domain from S1 to S4 here. Okay, so S1, S2, S3, S4, this cluster of four membrane spanning alpha helices, that is often called the voltage sensing domain. And we will see that this is separated from the other portion of the transmembrane domain here. So this is the voltage sensing domain. Okay, and as the name suggests, this is the portion that's actually going to be sensing the depolarization in the electrical potential difference across the cell membrane. Okay, so we'll be abbreviating voltage sensing domain down to VSD. Okay, so whenever we use VSD from now on, it will mean voltage sensing domain. Then the other portion, S5, the P loop, and S6. Okay, and I should just say this is S1 to S4 here. That's the voltage sensing domain. Okay, so I'll just color code that in as well. Okay, the next portion, which is S5, the P loop, and S6, often written like so. This is what's known as the pore forming domain. Okay, and this is the portion that obviously is actually going to form the pore. Okay, And you can see that the voltage sensing domain S1 to S4 and the pore forming domain S5, PS6 are separated by that S4, S5 linker. Okay, so we'll be abbreviating the pore forming domain from now on down to PFD. Okay, so S5, PS6 is called the pore forming domain, and we'll be abbreviating it down to PFD. Okay, right, so what we're now going to see is when we look at the more true structure of a voltage-gated potassium channel, okay, the pore-forming domain, S5, P, S6, is going to be hugely separate from the voltage-sensing domain, S1 through S4, okay, and what we've drawn here, this tetramer, really, this is only showing the pore-forming domains, the four pore-forming domains, okay, and we haven't actually put on the voltage sensing domains yet. Okay, so before I try and draw you a picture from this sort of three-dimensional angle here, what I'm going to draw you is an easier picture where we are just looking from above rather than from the side, okay, and that makes it easier to draw because I'm just now drawing a two-dimensional plane rather than trying to draw it at this three-dimensional angle. Okay, right, so I'm now going to draw a more true picture, okay, and in fact when you actually do look at the real thing, and I would advise that you go and have a look at the crystal structures on Google, okay, it does look like what I'm about to show you. The arrangement is how I'm about to show it. Okay, right, so initially what I'm going to draw you then is going to look exactly like what we've already got, and that's because what I have drawn you is exactly what the pore-forming domains actually assemble into, basically. Okay, so here we're viewing from the extracellular aspect, and here basically these are the four pore-forming domains of the four alpha subunits of the voltage-gated potassium channel, which are ascending to form the tetramer. Okay, now what I need to add on is the voltage sensing domains, and this is the new bit. These are sticking out from the sides, basically. Okay, and just bear with me whilst I draw this. Okay, so each one of these is this cluster of four membrane-spanning alpha helices, S1 through S4, for the four alpha subunits of the voltage-gated potassium channel. Okay, right, so this now is what the voltage-gated potassium channel looks like if you see it from above, basically. You have the four pore-forming domains in the middle here, okay, these four portions consisting of S5, P, S6, and then out more peripherally, you have the four voltage sensing domains of the four alpha subunits of the voltage-gated potassium channels. And you might think, oh golly gosh, that's really simple. So each alpha subunit of the voltage-gated potassium channel has its pore-forming domain lining the center, and then it has its voltage sensing domain sitting behind it. That's really simple. Okay, however, there's a subtlety here. This voltage sensing domain here is not the one that corresponds to this pore-forming domain here. This is from a different alpha subunit than this one. Okay, it turns out that the voltage sensing domain for this pore-forming domain is this one over here, basically. Okay, and this voltage sensing domain here, its pore-forming domain is this one here. This one's pore-forming domain is this one here. And this one's pore-forming domain is over here. Okay, so there's a subtlety here that the voltage sensing domains and pore-forming domains are not sitting next to each other, basically. Okay, so let me now show this. So we'll now start off by discussing the arrangement of the four different portions of the pore-forming domain, which I've separated up. Okay, so we've got the S5 helix, the descending P loop, the ascending P loop, and then the S6 here. Okay, so I'm going to show how they're arranged in the pore-forming domain portion here, and then I'll show you how the four alpha helices in the voltage sensing domain are arranged, and then we'll see how they link together. Okay, now initially we'll do this for one subunit, so here is one subunit, here is its voltage sensing domain, and here is its pore-forming domain, and then I'll complete it up for all the others. Okay, and hopefully we'll start to get an idea of how these alpha subunits of voltage-gated potassium channels are arranged to form this transmembrane structure here. Okay, right, so we're going to start off then with the portion that is in the pore forming region. Okay, right, so I'm going to start off by putting the portion that actually lines the pore in, and I've told you that this is that ascending portion of the P-loop. Now, unfortunately, it's in yellow, okay, and I'm very aware that that might not actually show up in this light. Okay, so I have just put a yellow dot here. I might outline it so that it shows up. There's that yellow dot, and that is corresponding to this ascending portion of the P-loop here. Okay, remember that's a linear portion of polypeptide, not a helix. Okay, and that is going to line the pore on the external side of the pore. Okay, it's not obviously going to line the pore all the way down. So if you were a potassium ion moving through this pore, whilst you're moving through the external aspect of the pore, you will be brushing against 4 of these ascending P-loops. So I might put these in here. Okay, so here are the 4 ascending portions of the P-loops for all of these 4 alpha subunits basically, and they are going to line the pore basically. So if you were a potassium ion, you would be brushing up against these 4 ascending portions of the P-loops basically, at least whilst you're on the external side of the pore. As you progress through the pore, of course, these ascending portions of the P-loop are no longer going to be lining the pore, okay, because they don't go all the way through the membrane, okay, and on the internal aspect of the pore, it's a different portion of the pore forming domain which is actually lining the pore. Specifically, we'll see it's the S6 helices. Okay, right, so that's where we'll start. That's the ascending portion of the P-loop. Okay, now let's put on the descending portions of the P-loop. Okay, so this is the ascending portion. The descending portion, in purple here, will be in this position, like so. Okay, so it will be behind the ascending portion. So basically, we are, remember, viewing this from above. This descending portion will descend down into the membrane, then it will loop back up. Okay, it will become this ascending portion, and the ascending portion is then the portion that's actually lining the pore of the voltage-gated potassium channel on the external side of the membrane. Okay, right, so that's the P-loop done basically. That's where the P-loop is positioned in these pore-forming domains. What I now want to add on to here is the rest of the pore-forming domain, okay, which is the S5 and S6 helices. So we'll start by putting the S6 helices in. So remember, S6 is coloured in here in blue, and S6 helices are going to be sitting in this gap here, okay, alongside the descending portion of the P-loop basically. Okay, so this is the S6 helix. Okay, so basically, again, remember we're viewing from the external side, so we'll be coming up the ascending helix, the ascending portion of the P-loop. Okay, that will be lining the pore, and then we'll be looping back over and going into the S6 helix, and then that goes all the way down through the membrane, and that is the portion that will be lining the pore on the intracellular aspect of the pore. Okay, so once the potassium ion has got past the ascending portion of the P-loop, okay, it will then get into the inner portion of the pore, and that will be lined by these 4 S6 helices. Now you can see that the 4 S6 helices are much wider apart than the 4 ascending portions of the P-loops. Okay, so in fact the pore gets much wider on the internal aspect than it is on the external aspect, and we'll discuss the significance of that later on. Okay, right. So finally, let me now put the S5 membrane-spanning alpha helices on this picture. Okay, so the S5 membrane-spanning alpha helices are right at the back, basically. Okay, they'll be in this sort of position here. Okay, so here they are behind the descending portion of the P-loop and the S6 helices. Okay, so the S5 helices are part of the pore-forming domain, okay, but they are not going to be they're not going to be actually lining the pore, basically. On the external aspect, that is the ascending portion of the P-loop's job, and on the internal aspect, that is the S6 helices job. Okay, right, so I said I was only going to do this for one subunit. I've actually done it for all 4 subunits at the same time. Okay, so this is the arrangement of those structures of every single one of the alpha subunits of a voltage-gated potassium channel in this pore-forming domain. Okay, and we've got 4 pore-forming domains here to making the entire pore-forming portion. Okay, so now what we want to see is for every single one of these pore-forming domains, where then is its other part, basically? Where is its voltage sensing domain? And we're going to start off with this one here. Okay, so I've said that this pore-forming domain here of this alpha subunit, this alpha subunit's voltage sensing domain is this bit over here. Okay, and I now want to show you the arrangement of the 4 membrane spanning alpha helices S1 to S4 in this voltage sensing domain. And again, I'll remind you, we are looking from the external aspect, so we're looking down on our voltage gated potassium channel. Okay, so now let me put the S1 to S4 membrane spanning alpha helices in. So here is the S4 membrane spanning alpha helices, and the S4 membrane spanning alpha helix. Okay, and what I'm going to do is I'm just going to put all 4 of these on, and then I'll explain how it actually makes sense. Okay, so there's S4, here is S3, here in red. Okay, then we have S2 here in blue. Okay, so I'll colour this one in blue in this position, and then we have green here, S1 here in green. Okay, right, so I'm saying that this voltage sensing domain here is corresponding to this pore-forming domain here, so this and this is a single alpha subunit of a voltage-gated potassium channel. So let's look at this picture and try and make sense of this, and remember we are looking from the external aspect. So you'll be starting off inside with your N-terminus on the cytoplasmic side. Then you'll have the T1 tetramerization domain, and then you'll be coming up into the first membrane spanning alpha helix. That is this portion here. So this is the first membrane spanning alpha helix. You're then crossing the membrane, and now you're on the external side of the cell membrane. You'll loop back down into the S2 membrane spanning alpha helix here. You'll go through the membrane. Okay, you'll end up on the cytoplasmic side. You'll loop back up into the S3 membrane spanning alpha helix, which is here. That'll be coming out of the cell membrane. Okay, you'll get onto the extracellular side, and then you'll loop back over into the S4 membrane spanning alpha helix here. You'll go down into the cytoplasm once more. And now somehow we need to have this connection between S4 here and S5 here. Well, I talked about the fact that this picture was misleading because of how small it showed this connection here, this S4, S5 linker. I said that that was much bigger than this picture implied, and indeed it is. So I will now show the S4, S5 linker. Now, this is where I'm kind of breaking with what this picture is showing, because remember, this picture is looking from the external aspect, and the S4, S5 linker is on the cytoplasmic aspect. But allow me that little discrepancy, and I've now put in the S4, S5 linker, but remember that that would really be on the cytoplasmic side of the membrane. Okay, and we're looking at from the external side of the membrane, so we wouldn't really see that. Okay, but just for conceptual purposes, there is the S4, S5 linker linking the cytoplasmic end of the S4 helix here to the cytoplasmic end of the S5 helix. You'll then come up through the membrane as the S5 helix here. You'll then have this loop on the external aspect going into the descending portion of the P loop here. You'll go down a little bit. Okay, you won't get through all the way in the membrane. You'll then loop back up, and then you'll come out in this ascending portion of the P loop here. Okay, which is the portion that lines the pore on the external aspect of the channel. Okay, and then you'll loop back over and you'll go down into the cytoplasm of the cell again through this S6 membrane spanning alpha helix, which is the portion that lines the pore on the internal aspect. Okay, so basically that is how a single alpha subunit in this voltage-gated potassium channel will be positioned, basically. Okay, so now let's complete the picture up and add these voltage sensing domains on for these three portions here. Okay, so this voltage sensing domain here, okay, this voltage sensing domain here, and this voltage sensing domain here, and all we have to do basically is rotate this round, okay, by 90 degrees each time. So there are the S4 alpha helices put on. Next, let's put on the S1 alpha the S3 alpha helices next. So here in red, here are the S3 alpha helices. Then we'll have S2 here in blue, like so, and then finally S1, which I'll put in green, like so. And then to really make this crystal clear, let's put in the S4, S5 linkers for every single one of the alpha subunits of the voltage-gated potassium channel. Okay, so this pore-forming domain here is linked to this voltage sensing domain here, and here is the S4, S5 linker. Okay, so that's one alpha subunit. Okay, this voltage sensing domain corresponds to this pore-forming domain over here. Again, I'll put in the S4, S5 linker. Then finally, this pore-forming domain here corresponds to this voltage sensing domain here. Okay, and here is the S4, S5 linker. So there, that now is a true picture of what a voltage-gated potassium channel tetramer looks like if you're looking from the external aspect, basically. Okay, and if you do go and look at the crystal structures, you will see how this faithfully represents the crystal structure. Okay, right, so that then is the arrangement of these different membrane-spanning portions in the actual tetramer, basically. Okay, and we'll be coming back to aspects of this picture later on. Okay, the next picture that I want to show you is another picture where we go back to trying to show this on this sort of an angle. Okay, so I stop with drawing it from above and I'm going to go back to showing it in this sort of three-dimensional angle where we're seeing it from an angle, basically. Okay, and the reason I'm going to go back to showing this picture is because I now want to show you the T1 tetramerization domains. This picture doesn't tell you anything about the T1 tetramerization domains. Okay, in the next picture I'll be able to show you the T1 tetramerization domains. Okay, and I'll also be able to put this into a more three-dimensional context. Okay, so let's do that now. Okay, right, so I'm not going to put the cell membrane on this time because that will just make it even more complicated. Okay, but here we'll start off by drawing the tetramerized pore-forming domains. So the tetramer of 4 pore-forming domains of the alpha subunits of the voltage-gated potassium channels, okay, which we know forms a nice cylinder, okay, a nice simple cylinder at the center here. Okay, so here are the 4 pore-forming domains all together, so this is this portion here. Okay, now what I need to do is make this more complicated by trying to put the voltage sensing domains on here. So here, this is going to be the voltage sensing domain corresponding to this pore-forming domain here. Okay, here is another voltage sensing domain which will correspond to this pore-forming domain we know back here. Okay, I'll add on another voltage sensing domain back there. Okay, like so, which will correspond to this pore-forming domain back here. Okay, and then the final voltage sensing domain on here, which will correspond to this pore-forming domain here. Okay, now before I put the T1 tetramerization domains on, I just want to color code this in. Okay, and don't worry, I'm not going to attempt to put all of these membrane-spanning alpha helices on. I just want to utterly make sure this is very clear in your head, okay, by color coding each of the alpha subunits in. Okay, so here is one of these pore-forming domains in red, and this is the corresponding voltage sensing domain here, which I'll also color in red. Okay, and now I'll color in the different alpha subunits in different colors. Now the reason that I want to do this is because I want to show you where the position of the tetramerization domains corresponding to each of the 4 subunits actually is. So I'll also color code the tetramerization domains in a moment. Okay, but first we'll just do it for the pore-forming domains and the voltage sensing domains here. Okay, so here is another voltage sensing domain of a different alpha subunit. Okay, so not this alpha subunit in red here, and its pore-forming domain is this one right at the back here, which we'll also colour in blue. Okay, and we'll have the next one in green here. So we'll have this voltage sensing domain at the back here in green. Okay, and it corresponds to this pore forming domain again at the back there. Okay, and then the final one here will have this voltage sensing domain in orange. Okay, and its pore forming domain is this one at the front here. Okay, which I'll also colour in orange. Okay, so if you haven't understood yet this concept that the pore forming domains are not next to the voltage sensing domains, hopefully that picture solidifies that in your head. Okay, right, so now what I want to show you is the tetramerization domains, the T1 tetramerization domains, which are sitting underneath. So all of this is sitting in the cell membrane, and I might be brave and just sort of try and put a bit of cell membrane in here. Okay, so all of this is sitting in the cell membrane here. Okay, now the tetramerized T1 tetramerization domains from all of these 4 alpha subunits of the voltage-gated potassium channel tetramer are going to be dangling down below the transmembrane portions, and they're all going to have tetramerized together. So let me now show this down here. Okay, like so. So here are these 4 tetramerization domains all tetramerized together. So I'll divide this now up into 4. Okay, right, so the question now is which one of these tetramerization domains corresponds to each of these 4 subunits. Okay, so let's remember where the tetramerization domain is on each of the 4 subunits. So it's the portion before S1. So where would we expect it to be? We'd expect it to be underneath the voltage sensing domain rather than the pore forming domain of each subunit, and indeed that's how it works. Okay, so what do I mean by that? I mean that the red subunit's tetramerization domain is this one here, okay, underneath its voltage sensing domain rather than its pore forming domain. Okay, the blue alpha subunit's tetramerization domain is here in blue, okay, again underneath where its voltage sensing domain is rather than where its pore forming domain is. The green subunit's T1 tetramerization domain will be down there in green, again underneath where its voltage sensing domain is, not where its pore forming domain is. And finally here is the orange subunit's T1 tetramerization domain. Okay, now of course they're not just going to be floating underneath, they are going to be attached. So I'll put in now the attachment. So here is an attachment between the red subunit's voltage sensing domain and its T1 tetramerization domain. Here is an attachment between blue subunit's voltage sensing domain and its T1 tetramerization domain. I'll try and put in an attachment between the green subunit's voltage sensing domain and its T1 tetramerization domain, and here the analogous thing for orange there. Okay, right. Now you can see that what this creates is a structure that is sitting underneath where the pore will open on the intracellular aspect. Okay, so if you imagine, if you are a potassium ion and you want to move through this channel, and let's say you want to move outwards, how are you actually going to gain access to the internal aspect of the pore? Well, you're going to have to go through these gaps here. Okay, can you see you're going to have to go in between this sort of hole here, this circle, okay, bounded on the sides by these connections from the voltage sensing domain down to the tetramerization domains here. Okay, bounded above by the transmembrane domain and bounded below by the T1 tetramerization domains, which are all tetramerized together. These holes, and you've got 4 of them around the sides, which are the holes that you have to go through if you want to then gain access to the internal aspect of the pore. These have a special name. They are called the lateral, meaning on the side, windows of the voltage-gated potassium channel, or some people will call them the lateral portals. Okay, and we will be using this terminology later on. Okay, so take note, those are called the lateral windows or the lateral portals. Okay, so just to finish up this picture then, what I will do is I will add on the finishing portions of the voltage-gated potassium channel alpha subunits. I'll just put on the amino termini here. Okay, so here are the amino termini of the 4 different alpha subunits of the voltage-gated potassium channel. Okay, so I'll colour code them in. This one's red subunits. Okay, this one is blue subunits. This one is green subunits here, and this one is orange subunits back there. Okay, and you could also, if you like, add on the C terminals, which will be dangling down from where the pore forming domains actually are. Okay, but I won't do that for fear of actually ruining the picture. Okay, right, so I think we'll have a break there. Okay, in the next video, what we'll firstly turn our attention onto is the huge diversity of voltage-gated potassium channel alpha subunits, and how this gives rise to a huge amount of diversity of voltage-gated potassium channel tetramers. And then we'll turn our attention to the mechanism by which a depolarization in the electrical potential difference across the cell membrane is actually going to lead to the opening of the channel.